thanks for that. That was much better than how I usually describe myself. So thanks for being here. So I'll have a few questions so I can maybe understand better where the audience is in terms of understanding. So the first question is, who actually codes in the audience? Okay, mostly people who code. Who's used multi-threading? Okay, quite a few. In C++? Okay, pretty good. And who's heard about the C# compute system from the keynote? Oh, I thought it was going to be the total opposite. Okay, so let's go about the C# compute system. So in 5.8, which now is called 17.2, 2017.2, we're planning to release a C# compute system. So what it is a way for games to use the other cores in a simple manner when available. So I'm going to go a little, in the examples after, I'm going to go a little more into what the C# compute system is and how it's built. Joachim Ante, our CTO, has made a presentation at Unite that goes a little over it. So and feel free to ask questions. If you raise your hand, I'll stop and then I'll answer. So in theory, right, obviously multi-thread all the things, nothing can go wrong with that, right? It's definitively just gonna be awesome. And a lot of people try and don't get the results they expect. And it can be confusing if it's the first time why it doesn't do what you want and why you're not getting the awesome promised performance. So in this talk, I'll do, I'll go back to the previous slide. In this talk, I'll do an overview, maybe 5 minutes, of what you need to be thinking about when you're choosing to multi-thread. Because that doesn't mean you need to or should. Then I'll talk about designing for C# compute, which is a specific implementation of a multi-threading API. If you're multi-threading in other ways, that doesn't necessarily apply. And I'll show the Boids demo where we've actually implemented C# compute for Boids simulation. So this is basically my favorite part. I can give you 2 minutes so you can read the first 2 bullet points. So basically, if you're doing optimizations, there is no free lunch. Multi-threading is not a silver bullet, and it's always a special case, because special optimization is a special case. So that's the first thing. Don't start off looking for the free lunch. You'll go hungry. It's not there. What you need to do is basically consider your specific problem, and then go from there. So quick example, so you really grok this, so you really can translate to actual design decision. This is the yellow pages. This is the yellow pages. If I'm looking for my name in the one on the left, a binary search will go very fast. If I'm looking for my name in this one, a binary search will not work very well. So although we always talk about algorithms, the performance is in the data, and the algorithm is in the data. So you got to go to what your game's data looks like, and to rephrase Andrew, how it transforms over time. And this is the same data. One is sorted, the other is not. So when you're thinking about structures of data, it's basically a transformation of data. You take the data and you sort it. You take the data and you put it in a BSP, a NOC tree, a quad tree, whatever spatial index or database system you want to use. But it's always the same data. And if you just chop it up, throw it in a pile, it's basically useless. So the first thing is look at your data, understand your game data, and then go from there. So one other thing to keep in mind is multi-threading optimization is a trade-off between effort, how much CPU you use to accomplish some amount of work, and latency. You want the results sooner. So here I'm saying single-threaded effort an optimal single-threaded algorithm is always going to take less effort than a multi-threaded algorithm. If you think of it as working together in a team, if you decided to do a table by yourself, it's going to take less effort because at the very least you won't communicate with somebody else to do it in half the time, working together. And usually you won't get to half the time, you'll get to 75% of the time, but you'll have used more effort. So it's a trade-off. So when you've got multi-cores, you're trading off effort, battery life, for execution latency. That is a fine trade-off in a lot of cases, but do remember you're making a trade-off, you're making a choice at that point. So does C# compute make sense for your game, right? So you've got a bunch of idle cores, then it makes sense to put them to work. And you must also have something that can be multi-threaded. Not everything multi-threads well. And if your data is a pile of shredded yellow pages, you might need to make a book with it before you can actually use it correctly. So you might need to redesign your game or design it first thinking of multi-threading at some point. So throwing in late multi-threading is something that can work, but that is much more difficult or more costly after the fact. Keeping in mind that the game design is where change happens, your engine design is likely where you don't want to rewrite all the time. So iPhone S, common platform right now, it's got 2 hardware threads. So one of them is the scripting thread, the others are the rendering thread. So if you throw off 6 more threads in there, you're actually going to reduce performance. You're going to increase the amount of effort, and you're going to have results that you will not expect. So if you've got a laptop like mine with 8 cores, then compute makes sense, and then you should use it. So then let's go into a little more what this means. So let's assume you've got a game. It's got either rendering thread time that you want to leverage. It's got some other idle core. Then you're deciding that you're going to leverage this to increase the simulation speed, the frame rate, or the experience. So you're going to put those guys that were not digging to work. So usually when we talk about multi-threading, we talk about in games there's basically 2 patterns that people see often. I've got a sound thread, I've got a rendering thread, and Unity already does that. There's a scripting thread, there's a rendering thread, there's a sound thread. So that there's already a system slicing, if you will, of the work. So you should not be likely, unless you've got something game specific, thinking of redoing a rendering thread. That makes no sense in this engine. So the data threading pattern is shaders are data threading. If you're familiar with shaders, the API forces you to make your data in a specific format. And that reduces the things that you can do, but it also makes it very easy to multi-thread and makes the data independent by definition. C# compute does the same kind of thing. So it's about reducing the design space to increase performance on a specific type of problem and architecture. So you have less option in C# compute, but you can do them much faster on multi-threaded architecture, just like shaders, the same trade-off. So Andrew talked about data-oriented design. That's something you'll see in the Boids demo a lot, so let's do a few lines on that. It's mainly used to optimize for a physical architecture. So it's very specific. So I'm saying it's going to run faster on this hardware. You might think that all hardware runs like this, but it's literally about making that choice. So you've got to be careful about what hardware you're thinking of. In gaming, on laptops, currently, that means you want to put things into array and process them in order. But beware about just oversimplifying and getting terrible algorithms. Design for cache coherency, put things in array in order. Group data physically in memory. C# structs inside arrays. That's basically the same thing. And you should not bank on multi-threading mono-behavior-based design. So if I have Boids, I have 10,000 of them, and each of them has a couple of mono-behaviors, then multi-threading that will be rewriting the whole thing. So I need to, from the get-go, think about my game, my systems in a different mindset. Data-oriented design works single-threaded as well. So it's good for multi-threading, but it's basically single-threaded as well. No free lunch still apply. Data-oriented doesn't mean it's best for all cases. If your data, a dictionary is good. You'd see hash maps being used in the Boids sample. So data-oriented design means I want this algorithm to run faster on this type of hardware. But if you're doing a lookup by doing a for loop in a huge array, that's a bad idea anyway. So you should have a dictionary will perform better. But if you have to loop through all the entries, then do it in a data-oriented way. So don't go overboard and think I'm doing all arrays and looking up things in them and all of that. So it's really about the balance anyway. Boids example. So I guess I could start with... So this is a pretty simple scene. Most of you have done worse, more complicated. There's one C# script. And basically all it's got is it's got a population of fishes. Each fish basically looks at its neighbors. And the basic Boid algorithm, if you're familiar with it, it's very clear. It tries to avoid the ground, avoid predators, and they try to band together. So a fish looks at its neighbors, calculates an average direction, position, and just goes to the next frame and tries to band together. Performance at this stage is, I think, over 50 on my laptop at this point. And you see what's happening a little on the profiler. Oh, I'm at 30. Okay, I added too many. So what you see here in the profiler is basically this Boids job that's happening on my free cores. Remember, iPhone 5, I have none of those hardware threads available, so I'm just getting diminishing return. It's not helping anything. On my laptop, Unity has decided that main thread, scripting thread, it's allocated for this CPU type a certain number of worker threads. So it's making a place for the work to happen, and it's matching hardware threads. It's not a software thread pool, which has terrible performance. And the job that are going in there are my Boids computation, right? And you can see in terms of the frame, if you imagine the Boid computation is thrown off to the jobs, and then the previous frame is rendered. At the beginning of the next frame, we make sure it completes, copy all the data back in, and then we loop over this. So it's basically a little like Andrew was saying about the system. It's basically stepping all the Boids through a previous frame to next frame type of pattern. So it's basically running all the transformation data on the Boid buffer, and it's double buffering them. Previous frame to next frame, previous frame to next frame. So there's a few things in code that this means. And let's look at code. I'm more familiar with that. So this is one C# file. It does everything you've seen. So the first thing is I have a struct for my Boid data. And it's a struct, first thing. And that's data that is actually in the game object transform. But I need to copy it. So my choice of multi-threading algorithm makes me use more memory because I need to right off the start. So it's not free. I've chosen to train memory for being able to work in the other threads. It's a struct. So you'll see mostly this file is all structs. So that's something to keep an eye on. Structs, why structs? Because structs are by copy. So you can't get multi-threading bug. If you give a struct to somebody, you've given it. He's got a copy of the struct. So you can't have access, which we enforce in C# compute. You cannot use in your data, just like a shader vertex array or pixel shader, you cannot put objects in there. needs to be a data type, and we enforce that when you kick off jobs. Because if you put a game object or a component in there, then somebody else could be accessing it, and you may get bugs. So when I was talking about domain restriction on the compute system, it prevents you from using objects as input to the compute system. And that prevents a lot of bugs. Makes it easier to use, but it does reduce your freedom. So you need to be using structs and planning on copying data around. So the Boids simulation is the main simulation object that has the basic parameters. Again, all public, no objects. And there's one function, and it works on one Boid at a time. I'll circle back to native arrays, which is a new type, I believe, for most of you. And float tree, which is another type that you have not seen before. Then the Boids simulation, basically for each Boid, calculates how it should steer and then saves the Boid output. So the Boid logic is happening in this function. So I'll collapse this again, and then we'll move on, and then we'll come back. The Boid's job and the Boid's transform jobs are the things you were seeing here in the profiler. This is the Boid job that calculates the steering for one Boid, or a collection. The job actually calculates a group of Boids in one section. And the Boid's transform job should be somewhere, there we go, is basically copying the data back to the source game object so that the renderer can pick it up. So as I said again, by choosing to go multi-threaded, I now have increased the amount of effort I need to put in. I need to copy back the data that's been computed into the transform instead of just doing it in place. So I'm actually doing more work in a sense, and putting in more effort. So the Boid's job it derives from the interface for iParallel4, which means it needs to implement execute for one Boid. And execute basically is what the job system will call from other threads and will do the work you want it to do. But to get results out of the job system in C#, you need to be able to read the results and to write data for computation. You need to give the system something to work on and a place to write results. And that's basically what those native arrays here. So as I say here, native arrays are a value type that are a wrapper around a native array implementation. And the value type is the C# interface. So when you copy a native array around, it doesn't copy the actual native data around. It's a value type so that can be used in the structs. And a native array also, if you've used the texture API, when you get pixels, you receive a copy of the pixel data that is held in the native video card driver or the native engine. You get an allocation and a copy, and when you set it, you get an allocation and a copy. So if you've done any high bandwidth C# to native marshalling, you know it's a very expensive operation. So native array are accessible from C++ and from C#. So the data here is looks like C# data to your C# code, but it actually, the memory is allocated in C++. And you need to dispose of this array. You'll see in this file there's a bunch of dispose. Those are new types. I believe they're in trunk for 2017.1. I do not know if they're public. I should have checked. But those new types will be available to customers soon. And expect to see more of them. Like this native multi-hash map, which allows you to get this on the other side. So again, needs to be disposed in your enable and disable. Unsable, dispose all the things.
Sorry? So native hash map is something that you use on the C++ side?
It's a way to put data into a structure that can be used both in C# and in C++ without copying it around, without marshalling. And it's the only structures that you will be able to use in the compute system. So if you put a new list, my value type, in the compute system, this will not be allowed. You'll actually get an exception. So for example, I have here, I have an object. Any object will do this. I go back to here. The minute this will be in, I'm going to get an exception. Invalid operation. We've detected an object by reference in your compute data, and that's dangerous, so we won't allow you to do it. The native array actually checks for multi-threading, so it is thread safe. That's why the handle that you get in C# pointing to the C++ structure, that is checked. So we know which native arrays are being worked on in which threads everywhere in the engine. So then we will disallow you from giving it to two jobs at the same time, for example. So we allow native array and native hash maps and the native containers that we will add because they will be inherently thread safe. And you'll get literally exceptions if you have two jobs working with them at the same time. So that's the security aspect of providing a multi-threading API and getting correct results and not debug for days because you've passed an array to two separate jobs and you don't know what's going on. One is overwriting the other. So this makes it impossible to set up that condition. Yep. So back to native array. So you then need a native array to copy your data into it to start, or to use it as the source of your data, like we do in the Boids simulation. But at some point, you'll need to set your transform back if you want to use it. You'll need to set your results back. So I'll go over that in a little bit. I could go over float tree. You notice float tree is, I have it here actually. It's a new set of intrinsics looking types. What they do is they look a lot like what you will get in HLSL shading language like swizzling, the addressing, just like shaders. You'll get the same math functions as well. And those types are recommended and I believe sometimes enforced, depending on what, in the compute system. Why is, if you use those types, you will get more performance. I'll go on why when I talk a little further on. But it is definitively also notation that a lot of people appreciate from writing shaders. You don't absolutely need to use them. We love them because that's basically, they're just good for streaming calculation and just batch operations. They're just good types for that. They have been optimized as well already for the computation. And Boids transform job, at the end, I need to copy back my transform data to the actual transform object. And here I've got a new sort of object you have not seen before, which comes with this system, which basically, if you want to write to a transform from another thread, but the main thread can write at any point in time from script to that transform, we need to validate that it's multi-threaded safe. So what will happen is, since you cannot use any objects in compute C#, you'll need to use object access. Expect texture access, mesh access, all structures that you basically use to as handles that will perform thread safe operation from your jobs into the native data. So that's basically the thread safe aspect of it. You cannot write unsafe code. The only way you can get to the transform is via transform access. And it is thread safe. And we enforce it in native.
Where's this transform coming from? Which object is that?
So in the example, you see the
Or sorry, I mean not with object because it's not individual. It's across many. But how do you
oh
associate?
you need to get it. Let's look at. So you actually get it from the game object transform in this version. So this is a development branch. You don't have that in the API yet. So basically, since the transform is such an object, it has basically you assign a transform to a transform access, and then you can use it as kind of a protected handle to that transform later on, and it becomes thread safe in that regard. So basically, it's just a smart handle that's going to be thread safe and can be used in jobs if you want to kind of understand what it means. So at setup here, when I had Boids, I basically get a way to for me to write multi-threaded from my jobs directly into the game objects. But that's the only transform possible from a transform access, a mesh access. So you need access handles to actually get to be coded by Unity and provided with the API for you to start using it everywhere. But it is one of the axes on which the API will grow. More transform access in more places. Mesh transform access. So they can use a mesh native data directly without marshalling from C# and read and write to it safely. So that's a little of where the system is going. Not sure if that makes sense to everybody. Feel free to ask questions. So that was the transform. And that's basically all there is to it except the scheduling. You'll see that in my game object, I have one. Let's start at the top. Basically, key down, something you've probably seen a million times, add a bunch of Boids. So here I'm making sure that the previous frame's simulation has been completed. So there's a new thing here you see, it's a job handle, and it needs to be complete. This will actually block if it's not, transfer work to the main thread if that job is uncompleted and unscheduled. So there's a lot of magic happening here. When you call complete, it's basically going to make sure that after complete, all the jobs work as completed. And basically, Boids is a struct, so newing has no impact. Just create a new job and new array, native array. Temp job is a specific allocator that we use a lot in C++. That's now available on those types. What this does is this array will actually use circular memory buffers that are actually allocated in C++. It's also going to be data that you will get exceptions if you keep handles on and depending on how you use it. But it's much faster than anything you could allocate otherwise. It can basically grow for free and does not need to deallocate. So when you push, you're basically pushing into a circular buffers where all those arrays are in. So you get basically that, but from C#. As you call add on this, it's basically just native mem copy to the right place, and it just carries on. The transform job is when I extract from the first job and copy back into the transforms. And here's simple double buffering. And then here's what you need to do to kick off a job. Once you set up kind of quote unquote your shader, if you think of it as shaders, C# general purpose shaders, remove the word shaders and you get C# compute, it's basically the same philosophy. So once you've set up your job, you basically just schedule it, you get a fence, and let's say you wanted the result right away, which would be a bad idea because you lose all your basically your multithreading. You will complete. After the complete call, it's done, guaranteed to be done. So before you actually want to access the data, or if you access a transform access, it's going to make sure that your job finishes. And here, for example, I can give an example. This job is scheduled after the first one. So it depends on the first job. The job system knows this. It's going to wait for the other job to finish, and then it's going to start scheduling this one. So it keeps track of dependency chains for you. So when you schedule, you keep the handle, and then you reschedule against the handle. Yes?
I have a question regarding the syntax. When you call complete at first at the top, you have a
Yep.
line where you say like dot complete, right?
Yes.
Is that line considered asynchronous? Like, is the rest of the code underneath it gonna get executed on the same like stack or something like that?
Yes.
Okay.
So the question is that line asynchronous? It's actually going to call into the job system. And just like graphics card APIs, the job fence is actually hash with a big number. And it's going to look quickly if it's done. It's basically a big integer comparison. And if it's not, then it goes into more work. And it's actually going to do the work of the job before complete returns on the main thread. If it's scheduled already and in process in another thread, it's going to block until that other thread finishes. So it is blocking.
So when you write this, you have to know actually that this function is going to block the execution of this stack, right?
Yes. The jobs, if I call this right after here, I've basically serialized the whole thing. And I will not get much benefits. So instead of at the beginning of my update, which completes the previous frame's jobs in case they're still pending, if I call it here, I'm going to serialize the whole thing.
In a sense, I know it's probably not that, but it's almost like a thread sleep call, right? Whereas
Yes. Is it almost like a thread sleep call?
I'm asking
It's more like wait for
right,
something.
because you
but
use
it's-
yield before doing those kind of calls, and that's the syntax that indicates that this line is going to be, asynchronous, right? If you use like a coroutine and you do like wait for a second, something like that, you have an indication there that this line is going to be asynchronous.
Yes. So the API there you need to know because it calls basically into C++. It's not using C# at all, and it's actually going to use, instead of just waiting, it's actually going to give itself to the job scheduler, because if instead of waiting, it should do work.
Right.
And if the job that it's waiting on is not scheduled, it doesn't want to wait for other threads to do the work, right? So in that case, you actually want that thread to jump into the thread pool and then come back when it's done the work that's required for that complete. Yes, it's the API. For example, when you call complete, you kind of need to know what the consequences of that are, and there are some. We've tried to make it very simple, but you still need to basically know a little under the hood what to expect, especially with the fences. And that's kind of a simple example, but still it's easy to run into less performance than you expect. And that's why you will go into the profiler, see what's happening, you will see in the profiler if you're waiting and what you're waiting on, so that will help you diagnose. So for example here, one of the things that you may not do as a mistake, for example, things that you may mishandle, is you might not give, those two jobs work on the same data. So you might not fence one against the other, meaning make sure that one is completed before the other one starts working. In that case, that will be a mistake, right? In most systems, that's going to be pretty dangerous. The way the native buffer work is that you're actually going to get an exception. We're going to say, no, you're scheduling this native data into multiple jobs. That's not going to actually happen on shipping build. That check is not free. But right now it will detect you've got an array, a native array, that's being used in two jobs at the same time. And then we'll just throw on you. Because that's a condition that is non-deterministic. That's not what you want. But you still need to kind of know about fences. But you'll get those exceptions if you mess around, you don't schedule your dependency tree or your work tree correctly. You will get exceptions. You'll get them right away, right? The minute I press play, I know I've messed up. And with the documentation, that helps you get to a working, stable solution much quicker than you might expect. The other thing about this code is what actually happens in the job, right? So we talked briefly about the native arrays, which are basically the only thing you can use, and what's in those structs, like this one and the float trees we've seen. So what happens when you write this code? It's not compiled necessarily with mono. This could be compiled with many things, and it's got a reduced feature set in terms of can't use objects. You've got a bunch of restriction on what can be sent to the job system. So the code that actually ends up in the job system, and you can kind of see attributes all over the place, and there's kind of a ints and all of that. It helps determine how to generate the code for this thing. So obviously C# code. That's the first thing that makes sense. So internally we've tried with a homemade compiler. And if you take float tree, for example, the accuracy requirements on float operations in C# are very high. So if you trade off accuracy for speed, which you often want, and graphics cards do, in the implementation, you can actually get ridiculous speedups. So the C# code may actually go faster than C++ even. We've got tests where this job code ends up going faster than C++, and compiled to native, basically. So it's pretty interesting if you start using this. As we define more compilers, more way to use the description, because this is basically a subset of C# that becomes kind of a compute language. If you use it in this way, we will keep working on the compiler backend, and you will get, for example, the math compiler just does magic that are not possible with when you have the, for example, the C# language requirements on accuracy. If you're doing a POW, it needs to be that precision. It needs to be, you need to respect that contract of API. So when we're going to be in compute framework, for example, in a job, you will be able, it's not yet in attributes, to define what type of compilation you want to happen to this. Do you want speed? Is it a particle? Is it a mesh processing? Do you need high accuracy or do you need speed? And that will allow the compiler to make trade-offs in terms of what binary code gets generated and how the maths are run. What kind of approximation do you get to most of your math codes, from sin to POW to square roots? And that can allow a lot of speed ups. But you need to make that choice consciously. If you just get weird accuracy problems and different across platforms, that's kind of not what we want. So we're working on making it predictable with accuracy level, but that's still work in progress. So the Boids simulation as you see it now should be in 2017.2. As you can imagine, there's a lot of testing and backend and front-end API that need to be worked to get this out in a way that is safe and will actually work for you guys. But basically, for some specific use cases, like this Boids simulation on my machine, it does go 8 times faster. And once the new compiler is in, it's going to go, the math of the transform, the lookup, and all of that will go even much faster. So that can get really interesting.
A couple of questions. On your mono behavior, you added a constructor. I thought it was forbidden on mono behavior.
It's very possible.
Is that a new thing? Yeah.
You've probably been coding Unity longer than I have.
And the second
Yes.
thing is that when you press A, you have some feature.
Yes.
On the Boids, is that do you have a huge overhead of resizing all those arrays?
Yes.
Yeah.
Yes, and that's not something we've tried. If you look at the actual implementation of the add Boids, it's basically very naive and it's very specific to the Boids simulation. So I would expect that compute in games that you will want to do, that's an ideal case, right? Boids are an ideal case. They can each do their own thing independently, just like mesh operations or particles, right? They don't interact as much, right? except from frame to frame. If you've got events, you've got complex game logic, then that's not going to fit well into this framework. So it really depends on what you're trying to do and how you design it so that it fits in the framework. Because the framework is restrictive.
But could you maybe allocate a maximum number?
Oh, for the array, yeah, there's many strategies that we could use, yes. That's just not been even a focus of that demo. It was more about showing the structure than making, and there's a hitch as well when you add.
But just to be sure, the system works really well when you have a fixed size of element. Right?
Yes, yes. And you will need to buffer when multithreading.
Okay.
So you said the system works very well when you have a fixed size of elements. Yes. And you will need to handle growing and shrinking compute buffers in an interesting way. Although if you use the temp alloc, then you could literally just consider that a free mem copy without an alloc if you fill it. But then a mem copy is not free, right? So you will have to consider how you store your data and how you put it into the job system. Native arrays can allow you to read accesses from it anywhere, but that doesn't mean that, let's say, the physics can use it directly. You'll need to set it on a physics component. You need to do all kinds of things with that data that you've computed.
I have a question regarding the data-oriented design. So I watched the talk, and there's a part of the talk where he talks about how to lay out stuff in memory.
Yes.
Like the order, like array of struct, struct of array.
Yes.
And do you have any kind of control on that kind of stuff with this API? Because I don't think C# allows you to do this kind of stuff with safety, right? Is it even pertinent? Is also a question.
Well, depending on what you do here in the structs and how you set them up, I would expect you could do most of it what you want. You could deconstruct your object, for example.
Right. You could build your own array and put x66.
Yeah, put component streams, for example, if you wanted. Depending on what you're trying to do, I would expect that would be kind of a second step. Once you've got something working with data that you can easily handle, then the float fours and all of those that swizzle easy and all of that come interesting when you need to use that type of packing.
In the back end, I expect the C++ code kind of already does that with the swizzling of the floats. That's why it's optimized that data structure, right? Because if it needs to only work on the x's, then you can access only the x's of, let's say, transform and pack them together in memory, and you won't have cache misses.
Yes.
To access that, right?
But so if you need to access only the x's of interleave data, XYZ, 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 we do not do any magic for you. You will need to put all your x's in one array and maybe switch around your things. Yes. But I've made tests on swizzling and vectorization, and the intrinsics you see float tree there, but there's quite a few there that you can use from, and I'm not sure which ones will be public, so I don't. But I've done tests where it's literally 60% faster by just using more of those, like taking transforms and just packing them. But it might not mean 60% depending on what percentage of your game it is and whatnot. I wouldn't go there first. And just as in for compute, you need to have a case for compute before you actually go and compute. Right? On an iPhone with no threads, basically, your main bottleneck might be the render thread. And then you've got the main thread with some free time. Well, you should single thread and there. But if you've got multiple platforms, some PC, then the job system is not, if there is no available job thread and you need to complete and nothing's happened, it's going to go on the main thread. So it's not terrible, but it wouldn't be the best strategy to use compute when you've got no actual hardware threads. So the platform you're working for will have a big impact. And if you're going to do stuff like packing your X's and your Y's and all, working on your data a lot, that is a platform-specific optimization. And it will behave differently in terms of CPU, PS3, PS4, of course no more PS3, but PS4 and whatnot, you get different behavior. So that will be something I'll keep at the end, because you might end up having to, if you do some of that for PS4, you lose on some other platform. So at that point, you probably want to do that at the very final stage.
Someone's going to probably try and do that and see if it's like a huge performance boost. But I'm thinking it's super interesting to see how it affects, you know. Like you said, it's a secondary optimization in a sense, right?
Yep.
And I agree. But I'm really curious to see how much of an optimization it could be, right?
Yes. So how much impact can you have with just writing with shader language intrinsics, right? Load, mul, and let's say taking four things at a time, loading them, multiply, unloading, and kind of trying to, let's say, stride your loop with kind of a batch. Let's say you've got 128 elements and you do them 16 by 16 because it cache aligns. That's going to work perfectly on the machine where it's supposed to work perfectly, and you might actually get terrible results on the one that the other one. So I would say wait for the compiler to do that for you, and if it doesn't, and if you've got a real problem, then fix it for the platform. I would hope our compiler will try to solve a lot of those problems. But 2017.2 is going to be first iteration. I will not bet on that compiler being yet strong enough for a first release. Maybe. Don't quote me on this.
Is there any way that you could send some jobs on the GPU with this system?
Is there any way that you could send those jobs on the GPU with this system? Of course.
Because it's mostly shader compute buffer. Right?
Yes. So you could compile this code to run on the GPU. The data is set up so that it can be consumed in that manner. Yes.
So do you have in mind maybe doing a compiler that would create the shader for you?
One would think that if we were smart, we would be making multiple compilers. Question?
Tell me when it's annoying without stuff, but
No. It's a question period anyway. So
well, I don't know if you're finished with the talk, that's why.
there we go.
I think I was also interested in can you send some work to the GPU?
Not yet.
Right, but eventually, like, it
Maybe
seems
not
like,
ever.
or maybe not ever, but it seems like you kind of took decisions that might.
No, but I cannot talk about that project even if we intended it. It's too far away
For sure, but it seems like you've taken steps that it's not impossible. That's what
We've taken steps so it's possible. Yes.
I'm not sure, but I think in OS X there's a lot of driver issues with compute shaders. Like I'm like a follow-up question to the answer you can't answer, but have you guys considered that it might not be possible if you try and send jobs to the GPU and the GPU doesn't allow you to access you don't have a compute shader driver available, let's say in OpenGL, because it's an older version. Are you just automatically going to like not compile it for, let's say, OS X on the GPU? Like, is it invisible to the user as well?
I would expect you will want to know
Right.
if we decide to compile in multiple ways for different platforms, is it invisible to the user? I would expect that the user will want to know. We have no specific plans on how you will know how it gets compiled. And I would expect that you will give compilation hints and probably at build time with attributes like you saw. We use a lot of attributes in that system. So you will get your struct and say, I want this on the GPU. But if you don't get it on the GPU, you'll probably get a build error or a warning. Because if it doesn't work on the GPU, well, of course, you've written it in C#. It works in C#. It works in C++. It works in assembly. It works on the CPU, basically. So, yes, I will expect we will warn, but we're not there yet.
You specify the number of cores that you want to use.
Yeah. Can you specify the number of cores you want to use? Yes. No. I'm not sure if there's an API to have the job system decide how many cores. But basically, the rendering thread is already taking a spot.
Yeah, sure.
and it's gonna stay there like this for a few releases. We may, with the render loops and whatnot, start moving things around, but I wouldn't expect anything soon. The main thread is gonna stay the scripting thread because it makes things simple for users. You don't need to think about threading most of the time, and it makes sense. The rest of the thread, then, it depends on the machine, literally. For example, PS4, you might get specialized compute units, so we could use that with compute shaders, although right now it's going to be general
But you can, what
CPU.
I mean is that, okay, for the boys, just use one core. Just one.
You cannot, you don't
False.
have currently from C# you cannot from C# specify how many core a job will use or the job system
The
will
limit,
use.
yeah.
So currently you have access to the job system, and it basically allocates one worker thread per hardware core, because you basically want to match the available work areas with hardware support. You don't want to have just threads, OS threads or whatever threads just hanging around. Those will be slow. So it's basically a fixed number per platform. And that's why I say it's always a call, whether you're going to try to leverage that. And to that point, it's literally, do you have idle workers on the side of the road that you want to, do you have free capacity is your first question. And then if you don't have any free effort, you don't need to multi-thread, you need to optimize something else to give you even space to do anything like that. So I definitively, as you're planning, working on your project, platforms and whatnot, it needs to be considered. But don't multi-thread all the things and hope for the best. It's going to be the worst. Yes. Any other questions? Oh, sorry.
Is there any push to expose any of the functionality to native user or native developers or native code?
So, is the question, are we planning to expose some of the native APIs directly?
Yes.
No. What we are planning is C# is going to remain the scripting API, and we want to expose more to C#, but not directly native. So the reason most people want to get to native quickly is usually memory management and the marshalling costs. If you're decoding a video and you're copying it into a texture each frame and you don't have access to the native memory, you're doing one extra copy and it's terribly slow. So with native arrays or native buffers, we want to give access to the native memory so you can actually write to it to C#. So you remove a lot of the performance bottleneck that will make you want to go to native, basically.
So does that mean that a native plugin could access the native arrays natively?
Not generally. That's not the direction we want to take the API.
Okay.
Ideally, we keep it much more C# because it has more power and it's much easier for us operationally.
Understood. But on the other side, when you have people who come with native plugins, they might need certain hooks.
Yes, and then I would definitively use that native plugin from C# and go into the engine from C#. To use C# to basically drive the whole thing. That's what I would recommend is probably more future-proof. As we get the new garbage collector, we get better at C#, we get better at everything. I'm expecting that the cost of working in C# will drop as well, the performance costs, which usually happen with marshalling data or garbage collection. But if you've got native arrays, you dispose those, they grow nicely, you've got full control of them, and you've got value types in them. So usually it's what I've seen in terms of performance, you're copying data or you're garbage collecting too much, and we expect we can fix those problems within the realm of C#.
Would you be able to use the API in editor or editor tools? Maybe?
Good question.
Sorry.
Could you be able to use the API in editor for editor tools?
Yeah, without using like
Currently, the job system cannot do that. We've been asked to do that, and actually that falls on my team. It's not on the roadmap for the next 6 months, but it makes sense. you don't want to process data, you don't want to do all those things, and it's kind of weird that you can only do it as a game.
Do you have any advice for people? Because Unity is a multi-platform, you can compile it to different platforms. You might have a game that has a mobile version and a desktop version. What kind of advice would you say to someone architecting everything that wants to take advantage of the threads on a desktop platform, but also wants to have a single code base without having too much duplication? That could also work on mobile. Right? You go the usual way with if-defs, and then you just don't execute a job system on the mobile and keep it single-threaded there.
Good question. It's in general terms, I will not have a strong opinion. Right, you might want to have assets that you strip out, things like that. But I would expect that, let's say, I would ask, what would you use the job system for? That will change, right? If it's a core part of your game, like AI, or you've got characters, so I would expect then that it's not a core part of your game. It's like beautification, making grass move. You have additional visuals that can be dropped with some kind of a level of detail kind of slider. Then I would expect you will want to just use that system to turn it off completely.
You would be encapsulated within that system itself. And
yeah, but that's just like off the cuff. Right?
exactly. It's just a design thing more than.
Yes.
So just go back to the previous statement. So that applies also to the native arrays, that they can only be used in game and not in editor code?
Do the native arrays can they be used in game only? No.
If I write editor code, I can use those native arrays.
Yes. They have not been tested in editor yet. They will have to be. The temp alloc that you saw is an in-game thing, because you can't temp alloc more than a ROM buffer and watch that so that there's no leaks, because it doesn't allocate, right? So they're not yet editor proof, I would expect. This is slated for September, so we're not at that point. The code is not there yet. We're working on it. But it seems reasonable to expect that you will get native arrays everywhere. Because if they're part of the API in some places, they won't be able to know that they're being used in the editor. All good?